Hello, Science Alliance. Hiya. I've done something quite foolish. So I finished Lego Story Show and there was about 20 minutes to go until this lesson, and my computer was saying, you've got to update in order to print anything, you've got to update. And I thought, that's a good use of 20 minutes. So I pressed yes. And now it's well past time for the lesson to start, and we're at this situation here. 6 minutes left. Can I talk at you about science for 6 minutes until we need to use the quiz? I think I can. I think it'll be absolutely fine. So welcome. You need, if you want to join in with this lesson, you need just like a normal knife, like a butter knife, not a sharp knife, and just a lump of Play-Doh or blue tack. It's the most tenuous practical ever because we haven't done any practicals really yet with electromagnetism, because I'm not assuming that you've all got electronics kits. So have that to one side, ready to go. A brief recap, and then we'll move into what we're doing today. So this is lesson 4, which is about electromagnetic induction. What we did last week was, what we've been doing for a few weeks now really, is we've been looking at how, we were looking at the motor effect, okay, which involves the left-hand rule, Fleming's left-hand rule. So we were looking at how, if you have current flowing through a wire, you've put electricity into the wire, you've got current which is flowing. If you put that into a magnetic field, then the thing that is carrying the current, like usually a wire, experiences a force. Do you remember that? So here I've got a north pole of a magnet and a south pole of a magnet, so the magnetic field lines are going from north to south. I've got a current flowing through this little loop of wire here, and we've been saying how we can use Fleming's left-hand rule, that if the current is, let's say we've just stuck our wire, let's look at this side of the wire, okay? So current flows, I know usually it doesn't, but we say, because of just history, current flows from positive to negative. So my current is flowing anti-clockwise around here. If I stick it in this magnetic field, I can use the left-hand rule to go, okay, point in the direction of the field. So I'm pointing in my hand awkwardly backwards, left-hand rule. So my first finger is pointing from north to south. Let's look on this side of the wire. The current is going from positive to negative. So the current is going into the whiteboard, and I end up with my thumb pointing downwards. So I know that this side of my coil, there's a downwards force on it. And if I do the opposite, which is a bit easier, this time the current's coming out of the board, right? Because it's flowing from positive to negative. So point in the direction of the field, current's coming out of the board, and this time my thumb shows me that the force on this bit of the wire is upwards, which works out, right? That's how motors work. You put a coil of wire, or a loop of wire into a magnetic field, we get a downwards force on one side, an upwards force on the other side, and it starts to turn. And that's how a motor works, and motors are incredibly useful. 3 minutes left, but it's good because I had this bit planned anyway to chat to you, so luckily it's working out well. Motors are really useful for loads of stuff, right? Like obviously in engineering, but if you've got a bubble gun, then you've used a motor before. This is a motor, so we've got batteries here. This is a source of electricity, right? There's a voltage across the battery which makes electrons flow in the wire. And let's say it's a really hot day and I want this fan to work. I make a current flow through the wire. This little thing here is a motor, so the thing in there, the coil of wire, experiences a force and turns around, and that makes the fan turn around. Yay! Cool. So we've got a current flowing through wire, and that produces a force, and that makes things go turny-turny, okay? So that's called the motor effect. You use your left hand to work it out. What we're looking at today is electromagnetic induction, which is very similar to the motor effect, but also completely the opposite. So what the motor effect is if you get a piece of wire, just a piece of wire, doesn't have to be a connected up circuit, just a scrap of wire, if you move it in a magnetic field, if it cuts through magnetic field lines, you see here, if you imagine this wire is in the whiteboard and I'm moving it up and down, I'm cutting through this magnetic field lines, you get a current to flow. Well, no. You induce a voltage. You induce a voltage. I'm doing spoilers. If it's just a piece of wire and it's not a continuous loop, you get a voltage across it. I have drawn a plus and a minus sign on here to show. If you haven't done my electricity lessons, you might not know what voltage is. It doesn't really matter. You can think of it as just one side of the wire is a bit more positive, one side's a bit more negative. Okay, that's what a voltage is, like a difference. So if the wire is moving, we get a voltage which is induced. And actually the voltage changes direction. So the positive and negative side change direction, whether the wire is going up or down. You use your right hand rule to work that out. It's very similar to the left hand rule. I'm not going to go into it. You can look it up if you like. I don't think you actually need it for your exams. So a few things to mention. The wire has got to be, or whatever the conductor is, has got to be cutting through the magnetic field lines. So if I just hold my wire like this and move it to and fro towards the North Pole and then towards the South Pole, that is not inducing a voltage because it's not cutting through anything. The wire's got to be cutting through the magnetic field lines. Okay, most tenuous practical ever. Can you get your blob of Play-Doh and your blunt knife, just put the Play-Doh on the table and cut it with a knife. Just like cut it in half. I told you to bring a blunt one, so I'm just going to use my hand so that you can see. Cut the knife in half with the Play-Doh. Now, I was really struggling to phrase this on Facebook, and it's not going to be better today. If you've done that, smush the Play-Doh back together again. Can you use the same equipment to make the same cut, but can you keep the knife still? No, I've said too much and made it too obvious. So you probably use the knife to cut the Play-Doh, right? Use the same equipment, make the same cut, but keep the knife still. What are you going to do? What are you going to do? This is me trying to not assume that people have electronics kits. Trying to make the lesson interactive. What are you doing? Is it too obvious? You're moving the Play-Doh, right? You can make exactly the same cut by keeping the knife still and pushing the Play-Doh onto the knife. Maybe this will stick with you if you're ever doing an IGCSE physics exam. Don't forget, you could keep the wire still and you could move the magnet up and down, and that would still be the magnetic field slicing through the wire, okay? Do you see what I did there? Yeah? Good. I think that's all. Oh yeah, no, of course, there's one last bit. We've talked about a wire moving in a magnetic field and you get a voltage induced across it, one end more positive, one end more negative. If you connect all the wire up, so you get a loop of wire, this is why I kept saying current by accident, because if a loop of wire, a complete circuit, is moving in a magnetic field, then you do get a current flowing. It looks a bit weird. We don't think of just a loop of wire as being a complete circuit. You would think that you had to have like a battery attached to it and light bulbs and things, but no, as long as the wire is completely joined up, you get a current flowing. And this is useful, well, it's useful in like one of the most fundamental things modern humans have access to. It's used in generators it makes electricity, right? So we've looked at the motor effect where if a current is flowing, the wire experiences a force and will turn. But if you can make a wire turn that doesn't have any electricity, doesn't have a power source attached to it, if you could just make that wire turn, you can get current to flow. So it could be that it's attached to a wind turbine, or it could be that it's attached to a turbine that's part of a dam and water's having to push through and spin the turbine that way. Or we've looked at in previous lessons on energy, how it could be attached to like basically a big turbine, a sort of big fan type thing. And if you burn coal, you turn water into gas and then the steam pushes on the turbine, and that's what makes the thing go around. So in those lessons, I just went, oh, and then the generator makes electricity. This is how it's making electricity. There's loads of coils of wire in there, and as they turn around, then current flows through the wires. It's happening right now. If you've got any lights on in your house, oh, I think, oh, ooh. Sorry, I've had a computer update and everything looks fancy and special and the colours are different. Wow. Yeah, no, I don't. I just want to skip all those bits and just get to the bit where I teach these guys the lesson, please. Thank you so much. Yeah, so I found a torch that was very cheap in a charity shop because it was broken. It was a torch with a little dynamo in it. So it had something that looks a lot like a motor, but actually is a kind of little dynamo generator type thing, but it's still coils of wire and it's still got magnets on the outside, and that was attached to it was supposed to be a ladybird. It's a bit sad now. It was attached to some light bulbs and it had this handle on the side, so there's no battery involved to produce the electricity. You just turn the handle really fast and that spun the wire between the magnets and that produced enough electricity to light up the lights. And it was a little bit broken, so I tried to fix it, and obviously it just ended up completely destroying it. I did attempt to attach it to a voltmeter, thinking that if I spun the dynamo really fast, you would be able to see that a little bit of voltage was produced. I don't think this is going to work, but let's give it a go. Oh, look at that! We house computer! Hooray! Lots of things. Installation. What are you talking about? I just did the installation. Anyway, I'll pull up your quiz now because you're quite ready for that. Let's have a look and see if this works. So I've got my little dynamo. Attach this voltmeter. When I spin it around, are we going to see? Oh, wow, look at that. Come on, it's amazing, she says. Oh, yes, brilliant. So there's no battery there. That is literally just wire moving in between two strong magnets. And we are inducing a voltage. How fabulous. Okay. IGCSE magnetism teacher copy. There we go. I'm just going to do that again because it's cool. Wow, just making electricity from nothing. Cool. Nature's brilliant, isn't it? Anyway, right. Okay, so very quickly I'll show you this picture of a generator, and then we'll do the quiz, which I think you're ready for. It's a really, really mean quiz. This bit first. If you've got the printouts, please ignore them. Ignore the printouts. Just turn away from the printouts. Just look at the screen, please, because I'm going to ask you about this later. Hopefully you've got the hang of this now. Here's two strong magnets with a magnetic field in between them. This little ring of wire here is called the armature. So the idea is that you somehow make the armature spin round and round, and because it's spinning round and round, it's moving, it's cutting through these magnetic field lines, a current starts to flow because this is a complete circuit. Now the problem is, obviously, if you just had wires connected to the armature going off, I don't know, to people's houses or whatever, they'd get all tangled up, wouldn't they, when it spins. So instead, you have these brushes and these brushes and these split rings here. So the brushes are connected to the armature and they spin around, but the brushes are just gently laid against the split rings, so current can flow through, but you don't get all these tangly wires. It's good, isn't it? Okay, quiz time. Right, this is really hard. I'm proud to say. The idea of this, I haven't done this quiz so that you can test if you've understood it really and just get them all right. There's 9 questions, so I'm thinking that probably I'll just catch you out maybe like 4 or 5 times, and then by the end you might be beginning to spot like how I'm trying to catch you out and you'll have understood. Here we go, some more brain exercise, this quiz. We have got a wire wrapped around an iron nail which is staying still. Can you tell me, is there a potential difference across the wire? Like is one end a little bit more positive, is one end a little more negative? And is current flowing? The answer is no and no, because it's a piece of iron, isn't it? It doesn't have a magnetic field around it. So this wire is not cutting through a magnetic field because there isn't a magnetic field. It's just a piece of iron, guys. What about this one? A piece of wire wrapped around a magnet which is staying still. Is there a potential difference across that wire? And is a current flowing? Got to be a bit careful, haven't you? The answer is still no and no, because the magnet does have a magnetic field around it, but it's not a changing magnetic field. So the wire isn't cutting through the magnetic field, so still nothing happening here. What about this one? We've got a wire wrapped around an iron nail, but the iron nail is moving to and fro, in and out of the coil. If an iron nail moves in and out of a coil of wire, is there a potential difference across the wire? Is current flowing? The answer is, it's still no, isn't it? A no, because this isn't a magnet. Oh, it's a lovely effect though, isn't it? Like that. The iron doesn't have a magnetic field. So iron is magnetic, like it's attracted to magnets, and you can turn it into a temporary magnet, but this thing isn't a permanent magnet. It's just, it happens to be a magnetic item, but there's no magnetic field around it. Do you get that? Is that okay from previous lessons? It's attracted to magnets, but there's no current flowing through this wire. The electrons aren't moving, and this isn't a magnet, so we have no magnetic field here. What about this one? You've got a piece of wire wrapped around a magnet, and the magnet is moving to and fro. Is there a potential difference across the wire? And is current flowing? Be really careful. You got it? So magnets obviously have magnetic fields around them. If the magnet is moving to and fro, then that wire would be cutting through the magnetic field. It is a changing magnetic field. So we do have a potential difference across that wire. This is electromagnetic induction. Is a current flowing? No, it's not, is it? Super mean. Because this coil of wire is not connected up together. It's just a loose bit of wire. So we've got a potential difference. We don't have a current flowing. And more special effects, because why not? There we go, written down, just what I said. The magnet has a magnetic field and it is changing, cutting through the wire, but the wire is not connected. It's not a complete circuit. Not a complete circuit is a great easy phrase if you were answering an exam question on this. What about this one? Is there a potential difference across the wire? Is current flowing? We've got wire wrapped around a magnet which is moving to and fro, and the two ends of the wire are joined together. There's no battery or anything. The answer is, well, we have a magnetic field that is cutting through a wire, so there is a potential difference, and it's a complete circuit. So yes, current is flowing as well. Hooray, we got there. What about this one? Is there a potential difference across the wire? Is current flowing? This is a bit tricky, actually. It's a bit mean if you haven't been to our electricity lessons, which were ages ago. You've got a wire which is connected to a battery. It's a complete circuit, and it's wrapped around a magnet, and the magnet is staying still. Have you got an answer? So some people yesterday on Facebook were saying no, yes, like there's no potential difference, but there is a current flowing. If you look on the batteries, reminder for electricity, well, look, one end that is touching the wire is positive and one end is negative. So that is a potential difference. That's what a potential difference is, and it's the potential difference, or the voltage, you could say, which causes the current to flow. So yes, there is a potential difference across this wire. Yes, current is flowing, but it's not electromagnetic induction. It's just a complete circuit which happens to be wrapped around a magnet. There's no moving magnetic field cutting into a wire, so it's sort of cheating. Oh, what about this one? You've got two strong magnets, a north pole and a south pole, next to each other on, let's say, a table. You've got a piece of wire which is going sort of from us into the page. And the piece of wire is moving up and down between two magnets. Is there a potential difference across the wire? Is current flowing? Oh, I think if I press down again, it's going to move up and down, is it? Oh, no. Just giving you the answer. Yes, there is a potential difference across the wire. Yes, because the wire is cutting through a magnetic field. But current is not flowing, right? Because that is not a connected up circuit. It's just a piece of wire. There, it's moving now. So it would be cutting through those magnetic field lines. So you do have a potential difference. That is what electromagnetic induction is, but no current is flowing. Is there a potential difference across this wire and is current flowing? It's pretty much the same situation, but this time the wire is in a loop. Loop of wire moving up and down between two magnets. Potential difference, current flowing. The answer is yes. There is a potential difference across the wire. And yes, current is flowing because it's a complete circuit. We've got a wire cutting through a magnetic field because it's going up and down. And it is a complete circuit, yes. So that is, I mean, it should be spinning around, but that would be what a generator is, basically. Oh, what about this one? Come on. An electromagnet moving in and out of a coil of wire. I'm pleased with this one. So you've got an iron nail, but this time the iron nail has got wire wrapped all around it and the wire is connected to a battery. So you've got current flowing through a wire which is wrapped around an iron nail. The whole thing is moving in and out of a massive coil of wire. Is there a potential difference across that wire? And is current flowing? Okay, so hopefully you can tell me straight away that there is no current flowing through this wire, because it's not connected to anything. Is there a potential difference? Yeah, there is, because this is an electromagnet, right? It's an iron nail, but you've got, we have learned in previous lessons that moving charged particles generate magnetic fields. So here, because there's a battery connected, we have a current flowing through this wire. Wherever you get a current flowing, you get a magnetic field around the wire. In this case, the iron nail's been put in to kind of amplify that magnetic field, if you like make it bigger. So the iron nail is in a magnetic field. So now the iron nail has become magnetic because it's in a magnetic field, and we've just got this is a big magnetic field here, and it's going in and out of the wire. So it's the magnetic field of the electromagnet is cutting through the wire. So, yes, potential difference. No to current. Was that the last one? Yes, it was. All right, here we go then. How much have you remembered of what I just told you about AC generators, how you make electricity? You've got the same diagram here, two strong magnets, a sort of loop of wire in the middle. Can you please label the slip rings, the brushes, the armature, the output and the input, and tell me which one of those is a trick and you can't label it because it doesn't exist? So, I mean, the slip rings are fairly easy, aren't they? Because there they are rings. That the brushes slip over, so the brushes weren't a trick either. The armature is there, that's the bit in the middle. And what do you get? You get an output, don't you? That's the whole point, is that a current flows and comes out and then goes to people's houses and things. So the one that was kind of a trick that doesn't exist is the inputs, because we're producing a current here. We're inducing a voltage. We're getting electricity. So you don't put anything in, I suppose. The input would be the... Well, I don't know. There isn't one. Okay, now on your printout, if you got that from my website, you've got a diagram that looks like this. Isn't it beautiful? We need to talk a little bit about this diagram. So I've said many times, there's two different exam boards if you're doing IGCSE physics that could write your exam. At the time of talking, in, February 2024, the Pearson people who write the Pearson IGCSE physics exam, they don't need you to know this. But the Cambridge IGCSE exam does need you to know this. So, but you're home educators, aren't you? Probably. So we all know that no knowledge is ever wasted. It's not about what do I need to learn. It's just interesting to learn it. So let's learn it. Okay. We need to think about when the voltage is at its peak and when the voltage is at its lowest. And I didn't do this on Facebook yesterday, but actually I think we should also talk about when the voltage changes direction. Basically, you've sort of got to understand how you get a little graph. New pens! How you get a little graph from this situation where a loop of wire turns in a magnetic field. So I'm going to try and do it. Right, so here we go. I'm going to write 360 degrees here, 180 degrees, 270 degrees, 90 degrees. This is voltage, or I should call it potential difference really, shouldn't I? This is, well, yeah, it changes direction, so I'm just going to leave it like that for now. So are you okay with the fact that if I just hold this loop of wire so that, should I do this? I think that might make it easier if I fold it in half and we pretend that it's actually in the whiteboard. Let's just look at this bit, okay, on the left-hand side. This loop of wire, which is going into the board. we'll say that this is at 0 degrees. And as it turns around, it hits 90 degrees, 180 degrees, 270, and then back to 0, okay? When this starts to turn, can you see that it is instantly cutting through wires, okay? If in the split second that it starts to turn, our bit of wire is going up and the magnetic field line is going across. So they're at 90 degrees to each other. They're really cutting across each other. They couldn't be cutting across each other more. So at that point, when our armature is at 0 degree, I put 0 there, when our armature is at 0 degrees, then our voltage is at a maximum, okay? We've induced as much voltage as we can across that wire. So I'm going to just, it's IGCSE physics, I'll put across it properly. So this wire turns, let's just focus on this little bit here, until there's a point where it's at the top. And can you see that in this split second where it's turning up there, it's actually moving parallel to the wire, to the magnetic field. It's sort of doing the same thing as we did when we just moved it to and fro. We said like there's no cutting happening there, so there wouldn't be any voltage induced, wouldn't be any current flowing. It's doing that, but like just for a split second. Can you see that? So that was 0 degrees, maximum voltage, and at the top it's at 90 degrees, how it was before, but it's going in the same direction as a magnetic field line. So that is when our voltage would be 0. Then, it gets a little bit confusing. It turns around, turns around, turns around until it's at 180 degrees, so it's at maximum again. It is at maximum, but actually we have had a change of direction. So again, I don't think you actually need the right hand rule, but I'm sort of going to have to do it. If you use your right hand, point with your first finger in the direction of the field, which is north to south. It's moving upwards, so our thumb's pushing upwards, and we can see that the current is flowing into the page, right? Whereas when we turn it around, if we do the opposite direction, we're still pointing in the same direction, the magnetic field is still the same. But this time it's moving downwards, so I need to turn around so that my thumb's facing downwards. Ow! And now the current is, now the current's sticking out of the board. It doesn't matter if you don't fully understand that, you can play around with it yourself at home, but our current has reached a maximum, but it's also changed direction, so now it's down here. And then eventually we get to sort of the same situation we had with 90 degrees, where it's 0 for a little bit, okay? And it is just 0, because it's moving parallel to the magnetic field, right? Just for a split second. So at 270 degrees, right, 90, 0, 90, we've done 180 because it's flipped over, nearly finished, 270, that would be at 0 again. And you see where I'm going with this. It gets back round to 360, it's done 360, which I guess is the same as 0, and suddenly it's at its peak again up here. Whew. So, you might have to explain, if we join this up, you might have to explain why when a loop of wire is turning in a magnetic field, if you look at the voltage that happens, then the graph looks like that. I am going to link you, in fact it's already there on my website. If you just search Theatre of Science, the website comes up straight away, go to the IGCSE section, and right at the top there's a pink button saying like further reading and past paper questions or something. If you click on that, then for this lesson I've linked you to a couple of very good videos explaining how a generator works, and it sort of shows you when it's moving, like how it draws that graph. But oh yeah, so what's beautiful about this diagram is that they've used 2 loops of wire. I mean, hopefully maybe you can see now why that is a good idea. They've got a loop which is like across and a loop that is upwards on the same generator, so that as they spin you never have 0 voltage. Is that okay? If there was only 1 loop of wire, then when it was up here you just suddenly have no voltage, like no current flowing. That wouldn't be very good. So you get another loop of wire. Where should I put it? Oh, here. And you put it across like this, and then it means that when that loop of wire is has no voltage induced and so no current is flowing, this loop of wire has just got to its max. So you've got a kind of constant output of electricity. Whew, right. That is the end of the lesson. Thank you so much for coming. Thank you for supporting me. If you are enjoying these lessons, you can send me £5 a month. If everyone was me, and everyone just kept meaning to do it, I would not have a job. I would be, well, I would, hopefully, but I'd be working in a school. It's only because people are chipping in to pay my wages that I can afford to have this as a job. So thank you very much. If you would like to support me, you certainly can. I'm just going to find my Facebook page, because when I'm live I always say, if you leave me a little hello on Facebook, then I will say hello to you. Yeah, if you go to my About section on YouTube, or you could search Coffee Theatre of Science. This website called Coffee is how I make money. People sign up to support me with £5 a month on Coffee, and I do all my lessons and give all the printouts. And for you lot, you get a further reading as well, where I studiously research past paper questions I think you should be able to answer, and find like all the best bits of the internet for whatever we're learning about that day, and put them all for free on my website. So if you think that that is worth £5 a month, then do go to my Facebook page or my YouTube channel and find this link to Coffee, or just search Coffee Theatre Science and it'll come up. And I'll even send you nice things. I will send you rainbow glasses and information about how they work. I've probably got no comments on Facebook now, and I've gone through all this faff. My computer isn't wanting, my newly updated and shiny computer really not wanting me to access the internet. It's just not interesting. Oh, here we go. Oh, yeah, here's all my tabs. Brilliant. Oh, computers. Let's have a look and see if any of you have said hello. There might be a couple of you saying, where are you? Has it started? You're very late, even for you. So we've got, I think next week we're going to look at transformers. Because again, when we looked at how you generate electricity, I just went, and then generators and then transformers. We will look at how transformers work next week, not the robots. Although husband is very good at drawing robots. He sort of draws transformers as like a paid hobby. So I might try and get some transformers posters from him. But no, different kind of transformer. And then we'll have one more lesson, I think, on how to use equations. And then that's it, we move on to radioactivity. Alice! Oh, hiya! Oh, yeah, okay, right. Oh, hello, Joaria. Hello, oh, thanks for coming. Thought I'd pop in. Oh, yeah, Alice is talking about alternating current, changes direction constantly. Does that mean the split rings don't have to exist? Because the current is changing direction anyway. Oh, that is genius. Okay, yeah, I will link you some more to that, yeah, because there are some things that we haven't said. We need to do a little bit of mopping up, but I'll leave it because people on Facebook haven't heard that, and that's a brilliant question. So we'll cover that next week. We'll have plenty of time for that. Okay, thank you two for bobbing in to say hello. I'm going to go, and I'll be back next week with more All Ages Shakespeare lessons and more IGCSE physics lessons. Thank you so much for joining me. Thank you for all your support. Just refreshing, but I think it's fine. Joaria and Alice, I think it's just you guys. I'll speak to you soon. Bye!